Okay, let's take a look at why we designed the active pickguard the way we did. So I had a standard Carvin Bolt-T guitar. It's very similar to like a Stratocaster, Fender Stratocaster. And here we can see the old pickguard. It's this piece of acrylic with 3 coil pickups. So the active pickguard starts with a set of ghost piezoelectric saddles. So these saddles have a small piezoelectric crystal embedded in them. You simply take 6 of those, mount them to a bridge, take that bridge and mount them to the guitar, and there we go. So we just needed to have a circuit board right here that'll take these piezoelectric pickups and do its thing. Now the question is, how are piezo pickups different than coil pickups? So we can kind of imagine we have a bridge at x equals 0 going to the nut at x equals L, and the kind of string goes in between each side. Now, if this side is fixed and this side is fixed, it's not hard to imagine, one way a string could vibrate. It could take this shape. If we take a freeze frame, it'll take this shape. But then we can imagine other ways that satisfy this fixed boundary condition. It can go, one full cycle of a sine wave, or it can kind of go up, down, then back up, and, end up here, and go on and on and on. Now, the question is what about this kind of shape? This is a very real world type shape. You imagine me kind of pulling up, at this point, the string kind of comes up and takes this kind of distribution. How do we explain this in terms of the other shapes, the sine waves? So it can be shown that any shape that you could possibly think of that satisfies the fixed condition can be written in terms of a sum of sine waves. The key is you've got to multiply each shape by some coefficient, each sine wave by a coefficient, and add them up. And the magic is figuring out what these coefficients need to be, but you can do it. Now, mathematically, we get this nasty equation. It's not too bad to write it down. So first, we start with our sine function. We sum up a bunch of sine functions, kind of from n from 1 to infinity. If we take the first mode, the first case, you imagine we have pi times x over L. Well, when L is equal to x, when we're all the way on the one side, we have sine of pi. So the first mode is a half sine wave, so on and so forth. The A of n then just simply represents the amplitudes of all those string harmonics. And this total term here represents the shape along the string. We have another part here. We got to remember that the string wiggles over time. In these pictures, we kind of took a freeze frame when the string is at its maximum position. But we got to know that this just wiggles over time, like so. And we write that as a complex exponentials. Engineers love complex exponentials, but this is just a sine wave, essentially sine, sine 2 pi, frequency times time. Now, let's take it one step further and position a pickup down towards the bridge. If we kind of pick an arbitrary distribution of harmonics, let's say this is a pluck. At the first mode, we're kind of about, the amplitude's about halfway. The second mode, we're about 80%. And say this third mode right here, we're at about 100%. Now, with the same exact pluck, but we position the neck, the pickup closer to the neck, notice we get almost 100% amplitude in the first mode, next to no amplitude at the second, and about 80% at the third. Now, this is assuming nothing's changed about the pluck. We simply moved the pickup. So if you take the analysis a little bit further, one can show that simply moving the pickup up along the string with the same initial conditions, you have a variable comb filter, where kind of the distance in between these combs is controlled by where the pickup is. We've changed nothing else about the pickup in the string other than we moved where it was. Now, how can this possibly work? How can a piezo work if there's no motion at the bridge? I've seen various discussions on forums saying, acousticians are crazy. they must not know what's going on because there's no motion at the bridge. So, how can piezo pickups work? Well, it turns out it's actually pretty simple once you understand how a piezo works. Here's the constitutive equations for a piezoelectric material. It's a big, scary matrix equation, but it breaks down and it's pretty simple. So let's imagine we apply a force to the top of a hunk of piezo, a force over some area. It's called a stress. This stress translates into, a change in length. It's very, very small because piezos are very, very hard. But there is a tiny bit of strain. Now, what the piezoelectric equations tell us, if there is a stress or a strain, we get some proportional electric field and charge distribution. So what that means is force maps to charge on a piezo and vice versa. That kind of ratio and the amounts, depend on these coefficients, which are actually matrices themselves. But all you have to know is, a variable force can kind of turn into a variable charge. Now, earlier we looked at wave shape kind of in terms of displacement y with respect to position x. You can look in an acoustics textbook and find this first order approximation of the downward restoring force can be written in terms of the first partial derivative of the displacement with respect to position along the string, and it's related by the string tension. So let's apply that to our shape equation we had earlier. Sine, that's easy, maps to cosine. Chain rule, we got to pull out, this junk in here. There we go. Now we're going to ignore for a minute. This is a completely time-dependent variable. So we're taking derivative with respect to space. So we can ignore him. He's just a constant. And here's the magical part. We're doing our analysis at x equals 0. Well, that means this whole entire term is 0. Well, cosine of 0 is 1. So what that leaves us as at the bridge, we still have a time-dependent part, but the force-dependent part is not dependent on frequency. It's just a simple set of a sum of these constants. So what that means is the resulting output from those piezos, there's not this inherent filtering, this comb filter, because of the pickup position. This means no matter what, we kind of get all of those harmonics along the string. With a bridge or neck positioned coil pickup, that's not necessarily true. The cool part about piezos, we kind of design them so they have their own modes and resonances, but we kind of pick them so their first mode is much greater than our audio range. So what that means is our charge response with respect to stress is very, very flat. What this means is we start with a nice clean signal that has everything we want, and then we can filter away what we don't want to kind of simulate those other pickup positions. Because we are electromechanical and not electromagnetic, there's no 60 hertz buzz. This is a really cool feature. The final result is that we can get these kind of nice acoustic guitar tones, electric guitar tones, and everything in between. Now, let's check out kind of the block diagram of the active Pickguard. So we have these piezoelectric pickups at the bridge. They have a charge output, meaning that they're very high impedance output, so we need a little signal conditioning. We bring the resultant signal into the kinetist through its nice 16-bit data converter, do our DSP with some computations, with some C code. We send the signal out the DAC. We go to some more signal conditioning. We need an anti-aliasing filter. I threw in a digital pot. Now, there's absolutely no reason to do single-ended. Balance line is much better, so we send a balance line out. Now, I use the Cat6 cable, and the reason I use Cat6 is you can open up any monoprice catalog and find it very, very cheap. It's shielded. There's lots of conductors. It's very, very nice. The kinetist also has an I2S interface, so we can send the audio out digitally as well over this Cat6 with an AES3 transmitter chip. You know, some other cool features of the Kinetis. It has these hardware touch sense inputs. We can make a control wheel, you know, that's a touch. We can have buttons that are touch. Freescale was so gracious to provide a touch sense library, so it does a lot of the configuration. It makes it easy. Of course, we got to have lots of fancy LEDs. Lastly, we got to program the thing, so I decided to mix in this open source Jtag interface. You can go to P&E's website, they have it there, give you all the schematics and source code. You know, I take that along with the native USB interface of the Kinetis, in case we want to do like a CDC interface or an audio class interface. We put it together in a USB hub that's on the Pickguard and send it out through this USB Mini B. So that's the hardware, and that's kind of the design of the Pickguard. Now we can look at, you know, how we actually implemented or actually carried out the design. So let's take a look at some of the design tools I used to make the active Pickguard. It is a custom circuit board, so I need a nice circuit board design tool. My preference is Altium Designer. I love their tool, has all kinds of cool features. The coolest feature being hit the 3 key and I get a nice 3D view. So it's really nice to design and integrate in the mechanical pieces. We can see the OS Jtag, my touch wheel with the LEDs, alpha, beta, gamma, delta, some patch selection, Kinetis chip, analog interface circuitry, even a mute button. So one piece that you didn't see in the demo video is kind of the other side of this, the receiver box. So I have a Cat6 jack here. Well, this has to go to something that feeds power and gets the balance line signal. So I need the receiver box, and here it is. Quick schematic. It's just a little circuit board, has an Ethernet jack, power adapter, some LEDs, and a nice Amphenol audio jack, which they so graciously donated. Now I can't just have a receiver board floating out in space next to my amp. So I got an Libre design and modeled a case. So Hammond Manufacturing makes these nice extruded cases. I had these end plates made by Front Panel Express. They do engravings. It's really cool. So let's look at the exploded view here. So we can kind of see this came right out of Altium as a step file. I can see my plates and everything I need. So Libre Design's cool. They have a version. It's great for makers. Let's get rid of this exploded view. So kind of the last couple cool pieces is these LEDs for set back a few millimeters. I needed some little light pipes. I had those 3D printed after I modeled them at Shapeways. And the other thing I needed was my old jack plate, because I don't have a 1/4-inch jack anymore. I had to cover up the holes, so I came in here and modeled a new jack plate. Also had this 3D printed Shapeways. They had a cool black material. I could, you know, have a little logo in there. So it worked out pretty cool. So it's a great time to be a maker. All these cool 3D design tools, circuit board, software, Code Warriors, cool, all kinds of free stuff. So I hope you enjoyed the video on the Active Pickguard project, and I'll see you later.